Chapter 7 deals with non-algebraic functions called transcendental functions. The first transcendental function that we're going to look at is an exponential function. Notice in the definition, the exponential function would be f of x is equal to a to the x power. Now notice the difference between these exponential functions and our regular algebraic functions is that the base is going to be some number and our variable will be the exponent. So a very easy example of an exponential function would be 2 to the x power. If we needed to graph this, since we do not know what it actually looks like, we'll need to go back and use the t-chart to help us figure out the shape of this graph. So putting in a couple of negatives, 0, and a couple of positives, that should be enough points to give us the general shape of this graph. Now in this unit you will need to use a calculator. There will be a lot of decimals and a lot of problems that you're not going to be able to work in your head. So letting x be negative 2, 2 to the negative 2 would be 1/4 or 0.25. Letting x be negative 1, that would be 2 to the negative 1, which is 1/2, which is 0.5. Anything to the 0 power, of course, is 1. If x is 1, we'd get 2. If x is 2, we'd get 4. And graphing, we would get negative 2.25. That's very small, so we'll just estimate negative 1.5, 0, 1, 1, 2, and 2, 4. Now, connecting the dots, we would have our graph. And if you'll notice, on the left-hand side, we get very, very close to the x-axis. The right-hand side shoots straight up. It is increasing, and this is going to be the general shape anytime your base is bigger than 1. Now let's try f of x is equal to 1/3 to the x. Again, let's put in a couple of negatives, 0, and a couple of positives to see what happens. If I plug in negative 2, we'd get 9. If I plug in negative 1, we'd get 3. Anything to the 0 power again is 1. If you plug in 1, you get 1/3, which is 0.3. And if you plug in 2, you get 1/9, which is 0.1. Now graphing this, we've got negative 2, negative 9, negative 1, 3, 0, 1, 1.3, and 2.1. Connecting the dots, we would have our graph, and if you'll notice, this time is completely opposite. The left-hand side is going straight up, the right-hand side is getting very, very close to the x-axis, but never touching it or crossing it. And this graph is decreasing, and this will always happen when your base is a fraction that's less than 1. Now, all the transformation properties that we had on the last test still holds true for our exponential functions. So if I was to ask you to graph f of x is equal to 2 to the x plus 3, you've got to remember when you add 3 to the variable, that's going to take it to the left 3 units. So we just did 2 to the x. If we take that and move it to the left 3 spaces, you would get the graph of 2 to the x plus 3. Likewise, if we had 1/3 to the x power minus 2, the minus 2 is going to take it down 2 spaces. Again, we know what the 1/3 to the x power is. If we take that and move it down 3 spaces, we would have the general shape of our graph. Now, one of the things that we're going to have to do with our exponential equations is solve them. The easiest way to do this is to get the term that has the exponent by itself, make sure your bases are the same, and if they're not, you have to rewrite them so that they are the same. If the bases are the same and they're equal, that means the exponents have to be equal, so we'll set the exponents equal to each other and solve from there. So if I get the exponent by itself, we'd have 25 to the x is equal to 125. Now I need my bases to be the same. One of them is a 25 and one of them is a 125. You should agree that 25 can be written as 5 squared, and we still have the exponent of x, and 125 can be written as 5 cubed. Now again, if the two sides are equal and the bases are are equal, that must mean the exponents are equal as well. So setting the exponents equal to one another, we can solve for x by dividing. X would give us 3 over 2. Let's try this next one. 8 to the y minus 1 is equal to 1/2. We already have the term with the exponent by itself. Now we need to change our bases. 8 can be written as 2 to the 3rd power, and we still have that y minus 1 exponent. 1/2 can be written as 2 to the negative 1 power. So again, if we have the left and the right hand side being equal, the bases are equal, so that would tell me my exponents would have to be equal. Now solving, we would distribute the 3. We would add 3 to both sides and divide by 3, and we would get y to be 2/3. This next example, both of them have exponents, but they're on the side by themselves, so that is fine. We can rewrite the 1/2 as 2 to the negative 1, and then you still have the x minus 3 exponent. We can rewrite the 1/4 as 2 to the negative 2, and you still have the exponent of x minus 5. If they're equal and the bases are the same, the exponents have to be the same. So I'll take both exponents, set them equal to each other, and work from there using our distributive property. We need to get those x terms together, so I'll add 2x to both sides and subtract 3 from both sides. So that would leave us x is equal to 7. 64 to the x minus 7 over 6 is equal to 2. Again, exponents by itself, we need to rewrite our bases. It might take a little thinking, but you should agree that 64 is 2 to the 6th power. And then you still have that exponent of x plus 7 over 6. And then on the other side, the whole number 2, remember, has an exponent of 1. So if your two equations are equal, the bases are the same, that tells us our exponents are the same. Using our distributive property, we can solve. We would get 6x plus 7 is equal to 1. Subtract 7 from both sides. Divide by 6. We'd get x is equal to negative 1. This next example, again, they both have exponents, but they're both by themselves. We need to rewrite the bases. The 5 you cannot rewrite. But the 625, if you'll think about it, you should agree that it's 5 to the 4th power. And then you still have the x as an exponent. Since the left and right hand side are equal, the bases are equal, so the exponents must be equal. I'm going to subtract 3x from both sides, and that's going to give me x is negative 1. Now, an application of an exponential function involves finding the interest. The formula, a of t is equal to p times 1 plus r over n raised to the nt power. Now, if you'll notice here, p is the amount that's invested. R is your interest rate. Usually those are written as percentages. You're going to have to change it to a decimal. N is the number of times it's compounded in a year. So they will tell you that it's compounded yearly, so N would be 1. Twice a year, so it'd be 2. Quarterly would be 4. So on and so forth. And then T is the time in years. Now make sure you notice it's in years, so if they broke it down to months, you would have to find that fractional representation for years. Alright, so looking at our problem, Sandy invests $10,000 in a savings account earning 4.5% annual interest compounded quarterly. What is the value of her investment after 3.5 years? Alright, so her principal amount was $10,000 that she invested. Her rate is 4.5%, but remember you got to change it to a decimal by moving the decimal 2 places to your left, so that would be 0.045. And you're dividing it by n. N's the number of times it's compounded. It says it's compounded quarterly, so that would be 4 times. Then we have to find our exponents. Again, 4 for n. T is your time. It was for 3.5 years, so we'd write that as 3.5. Now putting this into the calculator, I would take the time to go ahead and multiply my exponents together. 4 times 3.5 would give you 14. Now once you do that, you should be able to type it all straight into your calculator, and you should get $11,695.52. Now when you get to problems like this on Hawks, they will give you the formula, so you do not have to have it memorized.